Well, I guess people are still arriving. I don't see anybody here yet. Did we join the correct meeting? Canvas is giving me a hard time too, so maybe it's just that. Oh, okay, I see people are starting to filter in. I know that Canvas is being a little bit weird right now. It's taking forever to load anything. So I'm going to give just a few minutes to let other people start to trickle in before we begin talking today about our new topic, which is exponential functions, the object that we introduced at the end of class last time. We are going to spend today and then all of next week talking about exponential functions. And these are a super special class of functions. You're going to have a total of 3 homework assignments on them. And before we get into the material itself, I just want to explain to you how I'm ordering the homework here, because there is something that's happening a little bit outside of our normal sequence. I know normally our homeworks open on a Tuesday and they're due the following Tuesday. But in order to kind of try to force people to stay in time with the class, I'm opening homework 16 today, and it will be due next Tuesday. So I'll go back over this in just a second once more folks have arrived. So you will have to work on that between now and next Tuesday. And then on next Tuesday, we'll open the 2 remaining homeworks associated with exponential functions, and they will be due the following Tuesday, getting us back on our normal thing after the exam and spring break stuff. Let's see now. Okay, so we want to make sure we're being consistent with notation. All right, good. So it looks like people are starting to get in here. I think that Canvas issues this morning are going to continue to slow folks down, so I'll move at a gentle pace at the beginning. All right. So of course, and as always, welcome back to College Algebra. MAC1105, section 007. This is a lecture, and today is the 25th of March, 2021. Today, we will begin our work with exponential functions. Specifically, we're working with, I think it's homework 16. Yeah. But then there are also homeworks 17 and 18, which are to do with exponential functions as well. But today we'll just be working on the stuff associated with homework 16. Announcements. So the obvious one first, homework 16 opens today after class. It is due next Tuesday. At the start of class. So we've kind of gotten thrown off of our regular homework cycle of opening on Tuesday and closing the following Tuesday. I don't want to rush you through anything. So you had until today to complete homeworks 13, 14, and quiz 5. And so, I also don't want to leave you with nothing to do between now and next Tuesday. That would be a horrible waste of time, especially since today we are lecturing on exponential functions. So homework 16 is opening today, and you need to complete it by the start of class next Tuesday. I know that that's a little bit different than what we're used to. It's a little bit outside of our normal cycle, but trust me, it's the right thing to do here, because if you spend, whatever, 4 or 5 days not thinking about this stuff, and then you try to start the homework next Tuesday, for example, if I were to do that, then there would be a lot of time to forget things in there. And I don't think that's helpful or healthy. So I want you guys to begin working on homework 16 immediately. If you want to start working on it today, that's wonderful, but at least within the next day or two. And then make sure you complete it by next Tuesday. Any other announcement-y stuff? Can't think of anything. We're doing pretty good. So the roadmap from here, we've got 3 homeworks on exponential functions. So that will be from now till Tuesday, homework 16, then 17 and 18 will be the homeworks for next week, and there's an associated quiz. And then after that, we're going to talk about logarithm functions. Once we finish talking about logarithm functions, we'll be ready for exam 3. So exam 3 is going to cover this concept of operations with functions, the section on one-to-one functions and their inverses, the 3 homeworks on exponential functions, and the 2 homeworks that will be on logarithms. And we're probably about 2 weeks out from exam 3. So next week, exponential stuff, the following week, logarithm stuff, and then the week after that will be exam 3. I did go ahead, oh yeah, I knew there was something else. So I checked, and the test 2 reflection is up. Now I got an email, I think it was either early yesterday or late the night before, saying that they couldn't access the test 2 reflection. Has anybody been having trouble accessing the test 2 reflection? It should be there. I've triple checked everything and talked with the folks in, you don't need that. Talked with the folks in our IT department about the issue, and it should be resolved. But is anybody having a hard time still seeing it? I'm glad to see that Mark can see it. Can anybody not see it? Canvas is going slow, so I know it's hard to check right now. But if you're having trouble accessing the test 2 reflection, just let me know. And I will, of course, if you complete that, I will go in and give you that 3% bonus. So please do that. So if you go to Canvas and look under the assignments, you should be able to see it. That's the place to go. So let me say this. I know right now it is tricky to check because Canvas is running slower than Molasses. But given that it is visible to Mark, I think it should be visible to everybody. It's this. Oh, we're still just not getting anywhere. This thing's taking forever. If that loads while we're here, I'll show you guys. But for now, I think it's wise for us to just begin on the material. So last time at the end of class, we started talking about exponential functions. We kind of introduced the idea of an exponential function. But I want to go back over that, and I'm going to use an explicit example here. So you'll notice that this section has, this section and the following sections have a lot of word problems. And that's because exponential functions are super useful in modeling real world situations. Anywhere the kind of thing that happens next depends directly on the thing that happened before, sort of stochastic systems like that, tend to be modeled well by exponential functions. Let me first just give the example, the definition, and then we'll look at an example. So an exponential function is one of the form f of x equals c times a to the x, where c is a non-zero constant and A is a positive constant. So C and A are just numbers. The number A tends to be called the base, and the number C the number C is called the initial value. And the name initial value comes from these sort of application real world problems. I'll explain that in a minute. The number A being called the base is fairly natural here because you see in the expression A to the X, A is the base and X is the power. What makes exponential functions exponential is the fact that the variable is in the exponent. So a little note. What makes just like with all of our other problems, sometimes we'll use t for the variable, sometimes we'll use z for the variable. So I'm not going to say that x is in the exponent, I'm going to say that the variable is in the exponent. And remember, exponent is just another word for power, right? So this is like some constant times some other constant raised to the power of your variable. So the fact that your variable is in the power is what makes these special. It's what makes these called exponential functions. And these are totally different than any polynomial or power function or anything else that we've seen in the past. These form their own family of functions in the same way that polynomials form their own sort of family of functions. These exponentials form a family of functions, and they're a hugely important family. If you're interested in studying any sort of natural phenomena, they're almost always modeled by exponential functions. Those of you who are interested in going into some sort of engineering or some sort of hard science, your mathematical world there is going to be differential equations, which are equations that relate rates of change to one another. They describe how water moves down a stream, or how steam mixes with the air, or how a spring vibrates. All of those sort of things are described by exponential functions. They form the largest basis of solutions for differential equations. They form the largest family of models for real world situations, even in softer sciences like biology and social sciences. These things are hugely, hugely useful. Statistics really everywhere. If you're going to do any sort of quantitative work, there's no escaping the importance of exponential functions, second only perhaps to polynomials in their importance. And that's debatable. So why do we care about these things? Where do they show up? I can say all that shit, but I think maybe giving you an example is wise. I'll give you one example, and then I want to talk about things like graphs, and make sure that we're comfortable with sort of the basics that we want to be comfortable with when we talk about any family of functions. But first, an example to give you an idea. Let's see, you guys don't need that. Let's just move that. So an example. Have you guys, when I was in school, John Steinbeck was still revered by the majority of American literature folks. And there's this book called Of Mice and Men that pretty much everybody had to read. That book has two characters, Lenny and George. And one of those characters, George, is Lenny, is obsessed with this idea of getting a farm and getting some rabbits. So we're going to say on day 0, George and Lenny buy a farm, and bring with them one rabbit. So Lenny always wanted the rabbits, and when they would be in a difficult situation in this very cute novel, he would say, George, tell me about the rabbits. And George would tell Lenny about how one day they're going to get a nice big farm, and they're going to have lots of rabbits that Lenny can care for, and it'll be very cute. The book is actually very sad. But let's say on day 0, whatever, the start of the adventure, George and Lenny buy a farm and bring a rabbit. On day 1, a wild rabbit appears. And George tells Lenny, watch out. Every day after this, the number of rabbits will double. Because rabbits being rabbits, that's just kind of what they do. Now, every day might be a slight exaggeration, but whatever. So on day 0, George and Lenny buy a farm, and they've got one rabbit. On the first day they're at the farm, a wild rabbit shows up. So now they have 2 rabbits. And having 2 rabbits, the thing that happens is you get more rabbits. So every day after day 1, the number of rabbits will double. What we want to do is find a function I'll call it R of X, which outputs the number of rabbits on the farm at day X. All right, so R of 0 would be the number of rabbits on the farm on day 0. R of 1 would be the number of rabbits on the farm on day 1. R of 2 would be the number of rabbits on the farm on day 2. A few values for the function R have been specified in the statement of the problem explicitly. So we know R of 0 and R of 1. What is R of 0? How many rabbits were there on day 0? You can help me out here. Yeah, there's 1 rabbit, right? On day 0, they bought the farm and they brought with them 1 rabbit. So R of 0 is 1. Thank you, Jake. What is R of 1? How many rabbits are there on day 1? 2, right? Yeah. Sorry about that. 2, yeah, thank you, Sophia, because on day 1, this wild rabbit showed up and they already had the rabbit they brought with them. So now on day 1, we've got 2 rabbits. Here's the first one that's not explicitly given to us. We'll need to think about it a little bit. What is R of 2? How many rabbits are there going to be on day 2? Yeah, thank you, both Jacob and Sophia. We're told that every day after this, the number of rabbits will double. If we double 2, we get 4. What is R of 3? How many rabbits are there on the 3rd day? 8. Yes, exactly, the double of 4. And R of 4 would be 16. Every day, the number of rabbits doubles. So if I want to come up with a formula for the function r of x, we need to notice the pattern here. I'll go ahead and write down r of 4. R of 4 we said would be 16. These rabbits are doing what rabbits do. They're making more rabbits. What do you notice about these numbers? If someone gave you this list, 1, 2, 4, 8, 16, how would you describe those numbers? Think about what we're doing. We're starting to talk about exponential functions. So is there a neat way to describe these in terms of powers of something? Well, let me remind you that 1 is 2 to the 0. 2 is 2 to the 1. 4 is 2 squared, or 2 to the 2. 8 is 2 cubed. They're all powers of 2. 16 is 2 to the 4. So if you compare that with these inputs, we start to see an algebra pattern here. Maybe I don't know off my head how many rabbits there are going to be on the 100th day. But if you look at this pattern, you could tell me in terms of the powers of 2 how many rabbits there would be on the 100th day. So based on this pattern, on day 100, there should be how many rabbits? You don't have to tell me as an integer. Tell me in this notation. On day 0, there's 2 to the 0. On day 1, there's 2 to the 1. On day 2, there's 2 to the 2. On day 3, there's 2 to the 3. On day 4, there's 2 to the 4. So on day 100, yeah, there will be 2 to the 100 rabbits. Perfect. So it looks like r of x is 2 to the x. And this is an exponential function. That's what this is. Notice that this is an exponential function. C here and a here are the two constants we need to characterize this exponential function. The base, a, the thing that's being raised to the variable power, is 2. What is the initial value, c? What's the sort of coefficient here? Is there a number out front? Well, remember, anything is that thing times 1. So we think of this as 1 times 2 to the x. And the reason we call it the initial value or the initial condition is because that's where things started. In fact, if you take the general formula for an exponential function, c times a to the x, and you plug in x equals 0, you'll always get c. And that's why we call this the initial condition. So we would say here our answer is that r of x is 2 to the x. And if we were asked for the numbers a and c, they are these. And we just got here by looking at patterns. All right, we just listed out the first few outputs. And we noticed that they can all be written as powers of 2, that we're doubling every time we take a step up in x. Anytime you see that behavior, every time x goes up by 1, the output doubles, you'll know that your base is 2. You know that you're going to have something times 2 to the x. And then the number that goes out front here, c, is whatever your initial value is, whatever you started with when your variable was 0. Okay. So in your homework, let's see, I think I have it popped up here. Oh, other one. In your homework, you'll see a handful of problems like this, right? Where you're just given some data and you're asked to find a function that models that data. Now, you'll have to determine whether the data is linear or exponential. We've talked about how to model linear data in the past. How can you tell if a table is linear? Think back to exam 1 stuff. How can we tell if the data in a table can be modeled exactly by a linear function? Starts with S, ends with slope, right? Yeah, we gotta look at the slope. So if the data in the table has the same slope between any 2 points, then that data is linear. But exponential functions don't have a constant slope. So let's talk a little bit about the graph of an exponential function, and it'll help you see the difference between these things and the linear function. I'd like to go ahead and graph the function we have here. So think of it as a separate problem. But we'll use the same function. I'm going to sketch the graph of the function r of x equals 2 to the x by plotting points. What we're going to see is that unlike a linear function where there's a single constant slope, these exponential functions, they're curvy. Their graphs have a curve to them. So if you're trying to figure out if a set of data is linear or exponential, you should compute the slope between a few pairs of points. If the slope is always the same, no matter which 2 points you're looking at, then you're looking at a linear function. If the slope changes, then the function is not linear. In other words, if you have a curvy thing, then the function is not linear. And in this homework, you can deduce then that it is exponential. Let's make a table of values. Some of these we already know. Like when x is 0, we get 1. When x is 1, we get 2. When x is 2, we get 4. When x is 3, we get 8. So just based on those, we can begin drawing a graph. Here's Here's my x-axis, and this graph is going to be y equals r of x. I'll mark this as 1, 2, 3. When x is 0, r of x is equal to 1. So the point 0, comma 1, let me I'll mark this up here as 8. Which makes this 4, 2, 1. So we know when x is 0, r of x, or y, is 1. When x is 1, r of x is 2. When x is 2, r of x is 4. When x is 3, r of x is way up here at 8. So you see this curve, right? This is not a straight line. I'd like to see what happens at some negative numbers too. Now, of course, this wouldn't have anything to do with the rabbits anymore because we can't talk about negative time. Or, if we can, even then it wouldn't make sense in the rabbit context. But just for fun, if I plug -1 into this function, r of -1 would be 2 to the -1. What is 2 to the -1? Can we write that in a nicer way? Can we write this as a nice clean fraction instead of something with negative exponents? What is 2 to the -1? Yeah, 1/2. And so when r is -1, sorry, when x is -1, r of x is 1/2. Let's do one more. What is r of -2? If x is -2, what does this function give me? Well, it's 2 to the x, so this would be 2 to the -2. What is that? What is 2 to the -2? Again, same idea, as a nice clean fraction. What is 2 to the -2? Yeah, good, 1/4, right? It's the reciprocal of 2 to the 2. So if you're needing to compute this and it's not immediately obvious, remember that the negative here just tells you that you can make the power positive by shoving the thing downstairs. So 2 to the -2 is 1/2 to the +2. And 2 to the +2 is 1/4, is 4. So this is 1/4. All right, let's add these points to my graph. I'll have -1, 1/2. That's right here. And then I'll have -2, 1/4. That's like really small. It's like right here. And you can see a little bit more of the shape of this curve showing up, right? If x were -3, we would be all the way down at 1/8, which is so small it's hard to draw. So I'm not going to include it here. If I came over here to x equals 4, my function value would be 16, which is like already off the top of the page. So what does this graph look like? Well, do my best to sketch it in here. This point's nice and fat, so I sit on the line well, on the curve well. This is what this graph looks like. And as we run out here further and further, this graph wants to sit down on the x-axis. And this sort of shape, this is the general shape of a exponential growth function. The thing that's happening on the left here where the graph of the function is sort of settling down on some particular y value. We've seen that sort of behavior before. What's the name for this thing that's going on over here, the little blue dotted line I drew in? What sort of thing does that remind you of? Starts with an A. Yeah, it looks like an asymptote, and it is. This is a horizontal asymptote. And it's the line, in this case, it's the line y equals 0. When we studied rational functions, we saw this sort of behavior too. But remember, for a rational function, we always approach the asymptote on both sides. As you go off to the left or off to the right, the graph settled down on its asymptote. Exponential functions only ever approach their asymptote on one side, either as you run really, really far off to the left, like this, or if you were to kind of imagine flipping this whole thing over horizontally, then it would approach the asymptote over here on the right. Okay. You see what I mean about this not having a constant slope? Right? The slope between these 2 points is different than the slope between these 2 points or between these 2 points. It starts out really kind of shallow, and then it gets steeper and steeper and steeper and steeper. This is something that you'll notice with all exponential functions. They all kind of look really, really shallow on one side and really, really steep on the other side. In fact, the growth over here is incredibly fast. It does not have a constant slope. As exponential functions grow, exponential functions grow, they get steeper and steeper. In fact, they do this really fast. So like I said, the next point, if I wanted to graph the next point over here at x equals 4, I would need to double the height of this point. It would be off the page, right? Right up. So my next y value over here, the next point on this graph would be like way up, it'd be like here. And the next one after that would be twice as tall. It would be halfway into my kitchen. So these graphs, as they get growing over here, they grow really, really, really fast. The 2 to the x function, the height doubles every time you take one step to the right. Yeah, like from here to here, the height doubles. From here to here, the height doubles. From here to here, the height doubles. If this were 3 to the x, every time you take one step to the right, the height would jump by a factor of 3. Questions about this graph, how we came up with the table, how we identified the asymptote, any of these things. Again, to help with this asymptote, what we said is if x was equal to -3, the y value here would be positive 1/8. If x was equal to -4, it would be positive 1/16. Those numbers are getting closer and closer and closer to 0. Just for fun, let's take a look at this bad boy in Desmos. Because in Desmos, we can zoom in and out. I can give you a better feel. I can't type today. Here's 2 to the x, right? And it has all those points on it that we just showed. The graph looks just like our graph, but of course Desmos can show us more. So you see, as I wander further and further over here to the left, the y values for this function really are getting close to 0. They don't actually go to 0. And I want to contrast this with what you'll see in your TI-84 or whatever graphing calculator you're using. If I come in here and try to graph, so I hit y equals, that will bring me to this page, and then I just type 2, and then this power button here. That gets me into the exponent, and I type in x. So I've got y1 equals 2 to the x, so it's going to graph the function 2 to the x. This makes it look like there's a y-intercept right here, doesn't it? But that's just the resolution of the screen being poor, right? So on your TI-83, TI-84, it's going to look like this thing smacks into the x-axis, but it doesn't. Look in Desmos. It doesn't actually smack into the x-axis and stop. It keeps going forever and ever and ever in this direction. And no matter how far out we go, the red graph never crosses the x-axis, never smacks into the x-axis and stop. It just keeps going like that forever and ever. So don't be confused by what the graphing calculator shows you. It's just the limitations of the pixels, right? You can actually see the individual pixels here. You have a limited resolution, so it cannot show you the graph getting closer and closer and closer, at least not at this window size. If you were to adjust your window size or zoom in somewhere over here, then maybe you can see it a little better. All right. I want to look at one other graph of an exponential function, another simple one. And then I'm going to talk about the kind of 2 different types of exponential functions that exist. One of them, one of the families, is like this, a growing exponential, where as you go off to the right, the function gets bigger and bigger and bigger. Notice that this function is increasing everywhere. Anywhere as you go left to right, the function is always getting bigger. The next function I'm going to show you is a little bit different. It doesn't do that. So again, I want to sketch by plotting points. I'll just call it f of x this time. 1/2 to the x. By plotting points. So again, I'll make a table, x and f of x. If x is 0, f of 0 is 1/2 to the 0. And remember, any number raised to the 0 is 1. If x is 1, then f of x is going to be 1/2 to the 1, which is just 1/2. If x is 2, then f of x would be 1/2 to the 2, which is 1/2 times 1/2. That's 1/4. If x is 3, then we get 1/2 cubed, which is 1/2 times 1/2 times 1/2, or 1/2 to the 3. That's 1/8. So notice here, when I put in these positive numbers, I'm getting out these fractions, and they're getting smaller and smaller. Just like we did for the other guy, I want to look at some negative inputs also. If I feed this function -1, then my output would be 1/2 to the -1. What is 1/2 to the -1? Anybody? 1/2 to the -1? Yes, it is, Mark. Yes. In general, exponential growth is much, much faster than polynomial growth. Sometimes a polynomial might appear to grow faster at first, but the exponential will always win eventually. All right, if we're having trouble with this, let me come over here. 1/2 to the -1 is 1/1/2, right? That's what the negative power means. It means you shove that thing downstairs. Yeah. So the top here is 1, and then we flip the bottom, and this gives me 2. What about 1/2 to the -2? That's the next one we need. Well, this should be 1/1/2 to the +2. And 1/2 to the +2 we saw earlier is 1/4. So this is 1/1/4, which is 1 times 4/1, or 4. So this guy, 1/2 to the -2, that's 4. And if you extrapolate, if you use this table so far, you can probably guess what 1/2 to the -3 would be. One-half to the -1 is 2. 1/2 to the -2 is 4. Then 1/2 to the -3 would be, yeah, perfect, 8. All right, now I've got a bunch of points. Let's graph this bad boy. Okay. Looks like we need to go up as large as 8 again. And I'll mark this as 1, 2, 3, -1, -2, -3. If this is 8, then halfway down here is 4. Halfway beneath that is 2. Halfway beneath that is 1, 2, 3, 4, 6, 7, 5. Okay. So when x is 0, f of x, or y, is equal to 1. So again, I have the point 0, 1. When x is 1, we have f of 1 being 1/2, which would be half as tall as this 1. When x is 2, we're down here at 1/4, already getting very, very small, hard to see. I'm not even going to bother plotting the x equals 3 point, because 1/8 on this scale is super hard to see. When x was -1, the y value is 2. So, okay, -1, 2. When x is equal to -2, y is equal to +4. So we're up here at 2, 4. And when x is equal to -3, we're way up here at 8. So this time my curve looks like this. And of course, we'll continue on in this fashion, going smaller and smaller and smaller here. Again, we have this asymptote thing going on. Again, it is y equals 0. That's the line that this graph is approaching. And now over on this side, we're getting really big. So what you notice is every time you take a step to the right here, the size cuts down by a factor of 2 instead of increasing by a factor of 2. So this is an example of what's called an exponential decay function. The previous function is what's called an exponential growth function. And this leads us to our first sort of little fact. If the base a of the exponential function f of x equals c times a to the x is bigger than 1, then f of x is an exponential growth function, meaning it's always increasing. And quickly. If a is smaller than 1, like here where a is 1/2, if a is smaller than 1, then f of x equals c times a to the x is an exponential decay function. And these are always decreasing and quickly. So the base, the number a, the thing that's being raised to the x in your formula, that's what tells you whether your graph looks like this or like the last graph. Is it decaying, getting small really fast, or is it growing, getting big really fast? If a is smaller than 1, like here where a is 1/2, then you're looking at a decay function, and its graph will look like this. Decreasing, decreasing very quickly. If a is bigger than 1, like in our last example where a was equal to 2, then your exponential function will be a very fast growing function. We call them exponential growth functions. Another fact is that these all have the same horizontal asymptote. The growth functions will have the horizontal asymptote on the left. The decay functions will have the horizontal asymptote on the right, but they always have the same line, y equals 0, as a horizontal asymptote. Aside from telling us the number of bunnies on George and Lenny's farm, these functions are really good at telling us how many bacteria there are in a petri dish. If you inoculate a petri dish with a certain number of bacteria, and you know how long it takes for each little bacterium or cell or whatever to divide, meaning split into 2 other cells, then you can tell me how many there will be at any given time by building a function like this. Okay. So let's take a look, make sure we're not missing anything. Decreasing, decreasing. Okay. Yeah, all right. So I just want to kind of, oh, I shouldn't have done that. Damn. So we can come back to it later. I want to kind of summarize what we've said so far and tell you some more nomenclature, some more terminology. Get this back up so we can refer back to it. So an exponential growth function will always have a graph looking something like this. And an exponential decay function will always have a graph looking something like this. And you see they both have the same horizontal asymptote. They're kind of mirror images of each other. Here, we have exponential growth. So A is greater than 1. This is also an exponential function, so it can be written as c times a to the x. But here, we have exponential decay. So here, a is smaller than 1. Decay is just a word for getting smaller, right? Like we talk about things decaying as they go away. So the objects here, whatever's being measured, these y values are decaying. They're getting smaller and smaller, closer and closer to 0. Over here, we call this exponential growth because this function is getting bigger and bigger. Remember, we always go from left to right, always from left to right. So if the base is bigger than 1, you're talking about an exponential growth function. Its graph will look like this. And if your base is smaller than 1, you're talking about an exponential decay function. Its graph will look like this. Fun fact, the y-intercept here is always 0, c on both of these, where c is this initial value, the coefficient, the number out front. And when x is equal to 1, well, no, I'll hold off on that. But some terminology. Another name for the base, A, is the growth or decay factor. So some of your homework questions and exam questions will ask you for the growth factor or for the decay factor. The reason we call them this is because each time x goes up by 1, the output gets multiplied by the number a. All right, so f of 0 is c. F of 1 is c times a. F of 2 is c times a squared. F of 3 is c times a cubed. And to go from any one of these to the next, you multiply by a. So you know when you multiply by something, that thing is called a factor. If you multiply over and over and over again by numbers that are bigger than 1, that makes shit bigger. Like if I multiply by 2 or if I multiply by 5 over and over and over again, that thing will get bigger and bigger and bigger. If you multiply by a number smaller than 1, like 1/2, that number will get smaller, smaller, and smaller. That's why we call them growth factors or decay factors. And it's one of the most important things for sort of figuring out the general behavior of an exponential function. It's figuring out the growth or decay factor. Oh. My intuition is to talk now about growth and decay rates, but I want to make sure I'm going through these things in the order they show up in your homework. Let's send this to printing out. I'm gonna have to watch it again. So you see your first few things have to do with graphs, horizontal asymptotes, working with tables, describing the basic behavior, identifying exponential linear functions, all of this stuff we've talked about. We can solve a problem or two like that. Growth. Oh yeah, okay, domains and ranges. We can do that. Do we talk about growth rates here? No. Maybe that's in the next one. Okay, I don't need to hit you with that if you don't need it here. Yeah, okay. So we'll save growth rates and stuff for later. Let's work a few kind of standard problems just to make sure we're getting enough concrete examples in here. First, any questions on what we've described so far? Okay. Then I have one or two other things here. The domain of any exponential function, this is good news, is always negative infinity to infinity, or all real numbers. The range of an exponential function depends on the number c. If c is positive, then the range is the open interval 0 to infinity, like these pictures, right? If you look at the range here, you'll see these functions hit everything from 0 to infinity. There's nothing beneath the x-axis, it's all up here. But if C is negative, we haven't looked at anything like that, but while we're here, if C is negative, then the range is negative infinity to 0. Basically, the graphs above would flip over vertically. And then one important note, exponential functions never have x-intercepts. i.e., c times a to the x equals 0 has no solutions. As long as c is non-zero. Remember, c is not allowed to be 0. So these are some useful facts. And this stuff that we've shown now is everything you need to go through all the homeworks, all the problems in homework 16. I would like to solve just one or two kind of straightforward problems before I let you go, where we're doing some calculations, and then that will be the end of today. Does anybody need more time to write here? Okay, I'll hold off for just a second. Okay, if you do still need to copy, I'll ask that you take a screenshot just so we have time to solve one or two problems before class ends. So if you're still writing, go ahead and pause on that and take a screen cap, leave some space in your notes. You can come back and fill them in. But I do want to make sure we have enough time to solve some problems here. So I'm going to go ahead and turn the page in about 10 seconds. Okay. So let's find a formula for an exponential function f of x equals c times a to the x, satisfying f of 0 equals 3 and f of 1 equals 1. So you have problems like this in your homework. Towards the top here. Yeah, they ask you to find CNA. Sometimes they'll ask you to do it from the graph. So this one is actually very similar to the one we're doing right now. And sometimes they'll give you this information just explicitly, like we have here, right? Passing through these 2 points. So how do we get started with this? Well, first, let me just draw a picture, because this information could have come to us from a picture as well. It's nice to have both pictures in our mind. F of 0 is 3, so 1, 2, 3. They've given me the y-intercept there. And they've told me that f of 1 is 1. So these are the 2 points that I know to be on my graph. We know that these 2 points are on the graph, and we know that this should be an exponential function, c times a to the x. So can you tell me, is this going to be an exponential growth function or an exponential decay function? Just based on these 2 points. Yeah, good, right? The graph has to look something like this, because we're going down just between these 2 steps. Since f of 0 is equal to 3, we know that 3 is equal to c times a to the 0. And at a glance, it looks like we can't solve this because there's 2 sort of unknowns here, right? We don't know c and we don't know a. Those are the 2 numbers we have to find in order to say what this function is. But what is a to the 0? Three is certainly just 3. C, I can't do anything with this yet, but what is a to the 0? If I take any number and raise it to the 0, what do we always get? One. Yeah, thank you, Charles. All right, because any number to the 0 is 1. And c times 1 is just c. So 3 is equal to c. So c's got to be 3. So we can update f of x by plugging in 3 for c. We know now that f of x is equal to 3 times a to the x for some constant a. And now we just have to find the number a. Since f of 1 is equal to 1, we know that 1 is equal to 3 times a to the 1. All right, if f of x is 3 times a to the x, then when I plug in 1 for x, I should get 1 out. F of 1 is equal to 1. So when x is 1, the output is 1. And this will let me solve for a. A to the 1 is definitely just a. Now I can divide both sides by 3. And I get 1/3 is equal to a. So I now know c and a. C is 3, a is 1/3. So f of x is 3 times 1/3 to the x. Can I cancel the 3's? in this expression? Is this the same as just 1 to the x? Just to be clear, this is our answer. This is the final answer for this problem. But then I want to know, can I simplify it further? Yeah, no, we cannot cancel the 3's. Why? It's true that this is not the same as 3 times 1/3, but what algebra rule tells me that I'm not allowed to cancel those 3's? It's the, yeah, order of operations, right? PEMDAS. Parentheses come first, then exponents, then multiplication, then division, then addition, then subtraction. So because the 1/3 is in parentheses and being raised to the x, we always need to think of this as coming first, then multiply by the 3. So because the 3 is outside the parentheses, not being raised to the x, the 3 and the 1/3 can't interact because parens and exponents come before multiplication in my order of operations. Okay. The whole curve here looks like this. This is an exponential decay function. Its graph has this sort of shape. And we could have given you this graph instead of giving you this information and asked you to find the function, because this graph has exactly the same information as these points. The last thing I'd like to leave you with here is a little review of some rules for exponents. How are we doing on time? Ooh, we're a little bit over time. Okay. So quickly here, let me impart some rules. Hopefully this is review. But it's good stuff to have. First, anything to the 0 is 1. For any a not equal to 0, a to the 0 is 1. We used that here. Second, if I want to take something like a to the x and multiply it by something else like a to the y, when you multiply like bases, you can add the exponents. Kind of similar to this, if you are dividing like bases, you can subtract the exponents. Another useful fact along these lines, a raised to the negative x, we used this a few times today, is 1 over a to the positive x. And then one more, if you want to take a to some power and raise that whole thing to another power, that's the same as having a to the product of those powers. We will use all of these quite a bit, especially in the next homework. This one is going to be very important. We're going to need to use this in both directions, going from things like this to things like this by factoring the exponent, and going from things like this to things like this in order to simplify. But all of these rules will be super duper important for us down the road. So again, I'm hoping everybody is familiar with this sort of thing, but in case you haven't seen it in a while, I think it would be wise to add this to your notes. So if you get stuck simplifying or working a problem, you can look back at these rules and ask, oh, can I use any one of these here? All right, that's it from me for today. So please work on this homework 16. Make sure you get that knocked out. If you need more time on homework 15 or quiz 5, which came due today, you can Canvas message me requesting an extension. I'll be happy to grant them, but you do need to ask. And then on Tuesday of next week, remember homework 16 is going to be due. So please get this done before next Tuesday. And then next Tuesday, we will continue talking about exponential functions. We'll start solving some slightly more complicated problems involving functions of that type. Any questions for me before we head out for the day? All righty then, I hope you guys have a lovely rest of your day. You can always come by office hours or Canvas message if you do think of anything you want to talk about. Otherwise, I'll see you all next Tuesday.